In this lesson, we're going to look at complex numbers. You may recall from previous math classes that complex numbers is really a combination of real numbers and imaginary numbers. In fact, complex numbers are all the numbers that we have so far. So a complex number can be written in the form of a plus bi, and we can represent that on an xy coordinate plane, where x is called the real axis and the y is the imaginary axis. Now, I know a lot of people hear the word imaginary and think, well, how could it have a real-life application? For those of you who want to be electrical engineers, I assure you, you will be using imaginary numbers and this complex plane. The first of all, we need to define the magnitude, or the modulus, of a complex number is the distance from the point AB to the origin. And that is our formula. Look familiar? It's just the distance formula. And notice we have absolute value signs around z. We're going to have the positive distance. So let's look at the first example. We want to plot the point in our complex plane, 3 plus 2i. So positive 3, out 3 on the real, up 2 on the imaginary. So it's just plotting points like you always have. It's just that this would be the positive part and the negative part of the real number, which is the a part, and then this would be plus and this would be minus of the imaginary part. Now we want to find the magnitude, or the modulus of z. Now just remember, that's just the distance formula, so that's what we're finding. So of course, it's just the Pythagorean theorem. So we have the modulus of z is equal to the square root of 3 squared plus 2 squared. You're not involving the I whatsoever. It's a distance. The I is on the imaginary plane, or the imaginary axis, and we're just looking at the distance. So we have the square root of 9 plus 4, which is the square root of 13. That's all there is to it. Don't make a big deal. Now we need to look at how we can convert from rectangular form, which is a plus bi, to polar form. Polar form is this. Of course, polar has r's and thetas, so r times the cosine of theta. Remember, cosine deals with the x value, and sine is the y, so again, this is the real part. We have that I, which is the imaginary part. You also can shortcut that cosine I sine by writing it as cis. That's not a new trig function. That stands for cosine I sine theta. Right, so we want r to be positive, and we want theta to be between 0 and 2 pi, or if you're in degrees, from 0 to 360 degrees. So example 2 says write in polar form 3 plus 2i. Now that's the number we just found up here, the modulus. So we want to express the angles in degrees. So for polar, we need to find r, and we need to find theta. Well, r is the distance from the origin, which is the same as the modulus or magnitude of z. Well, since we found that right here, 3 plus 2i, we don't need to do that again, the square root of 13. But what's theta? Kind of come back to this picture. That's theta. Well, we know that the tangent of theta is opposite over adjacent. So we could have the tangent of theta would be 2 over 3. Or the I part over the real part, or the y over the x, just like we have defined it many times. Right? So now, since we want our angle in degrees, you want to pick up your calculator, make sure it's in degree mode, and we're going to say theta is the inverse tangent of 2/3. And you can round your calculator. I believe I got 33.7 degrees. Now I'm not quite finished. We need to write it in polar form. So we can write it with the cosine theta, I sine theta, or we can do the shortcut. So we have z equals r, which is the square root of 13, the cosine of 33.7 degrees, plus I times the sine of 33.7 degrees. Or we could have the square root of 13 times the cis, and remember that's just cosine I sine, of 33.7 degrees. Either one of those is acceptable. We've expressed our answers in degrees and we've written it in polar form. So let's look at this next one. Write in polar form. Now this one didn't say we have to graph it, but let's just go ahead and look at that graph. I think it'll help. Remember, this is the real part, this is the imaginary part, right? So -3, we're going to go out -3 on the real part and up 5. So that's our point. And so if we're looking for polar form, we need to remember we need r and theta. Well, r is this distance and theta is that angle, right? So we need an angle in degrees, so that's going to be between 90 degrees and 180 degrees. So let's find r. So first, r is the modulus of z, which is the distance, so that's the square root of -3 squared plus 5 squared. So that's r. So now theta, we're going to use the tangent of theta is the imaginary part divided by the real part. So I have theta is the inverse tangent of 5 over -3. Again, you want to put your calculator in degree mode, punch that in. What does your calculator tell you? Approximately -59 degrees. Is that correct? No. Where's -59 degrees? It's down here in that quadrant, right? I need an answer between 90 and 180 because I need that angle. So what do? I need to add 180 degrees, okay, because that's a line, and I get approximately 121 degrees. So that's why graphing it will maybe help you know what quadrant you're in when you're writing the correct answer. So if I want this in polar form, I'd have z equals r, and I'm going to go ahead and write it as that cosine I sine cis of 121 degrees. Be careful of your quadrants. The next example gives us a polar number and asks us to write it in rectangular form. That's actually pretty easy. All we need, remember, we need it in rectangular form, a plus bi. So all we're going to do is we're going to use the distributive property. Right? So get your calculator out, but what mode does your calculator need to be in? It needs to be in radian mode. Right? So we're going to multiply 3 times the cosine of pi over 10, get that answer, and then we're going to multiply 3 times the sine of pi over 10. All right, so your calculator's in radian mode. Punching that in, you're going to get some really ooky decimals. So let's just round to the hundredths. So I got 2.85 plus about 0.93, and don't forget your I part. And yes, that's all there is to it. But let's go back and see, well, where would this be in our coordinate plane? Well, we would go almost over 3 and up almost 1. So definitely in the first quadrant. Well, where's pi over 10? I know, no one thinks in radians, but if we change pi over 10 to degrees, we would multiply by 180 over pi. That's the conversion. And so that is 18 degrees. Does that look about 18 degrees? Yes, it does. So just to kind of give you a visual representation. But this is all you had to do to go from polar to rectangular is just the distributive property. So now we know what complex numbers are. We now need to know how to multiply and divide them. It's actually pretty easy. So if we're given two complex numbers, in order to multiply them, we just multiply their r values and add their theta values. If we want to divide, we would divide their r values and subtract their theta. Now remember, subtraction is not commutative, order matters. So you want to make sure that you have the top one minus the bottom one. So in example 5, we want to multiply these two values and divide them and write our answers in rectangular form. So let's go ahead and do that multiplication. So the multiplication says to multiply their R values. So let's see, I've got a 2 times 6, and yes, I know that's 12, times the cis, or cosine I sine, of their theta values added together. So this would be z times w is 12 times cis of 280 degrees. Am I done? No, because it says to write it in rectangular form. So let's go ahead and write this out as 12 times the cosine of 280 degrees plus I times the sine of 280 degrees. So if I want to write this in rectangular form, just like on the last example, I'm just going to use my distributive property. What mode does my calculator need to be in? Degree mode, right? So I'm multiplying 12 times the cosine of 280 degrees using my calculator, and I get about 2.08. Then I'm going to multiply 12 times the sine of 280 degrees, and I get about negative 11.82, and remember that's your I value. And again, if you want to visually check that out, if I went to the right 2 and down almost 12, I'd be in quadrant 4. 280 degrees is in quadrant 4, so I feel comfortable about that answer. So now we're going to divide. Okay, so I'm going to divide their R values, and I want to subtract their theta values. So I have 1/3 times the cis of negative 120 degrees. Now, negative 120 degrees, remember, is also 240 degrees. Now, yes, you could leave it as negative 120 if you're using your calculator, but what if I asked you right here not to use a calculator, as in I don't want decimals, but I want the exact values? Why would I want that? Well, because I'm a math teacher, and I know 240 degrees is something you should have memorized in your trig class. What is the cosine of 240 degrees? It is negative 1/2. What is the sine of 240 degrees? It's negative square root of 3 over 2. So yes, going back to trig, what quadrant you're in, reference angles, however you want to know, but you've got to know those exact values. So again, multiplying that out, that's going to be negative 1/6 minus the square root of 3 over 2 I, and that is what their quotient, or their division, equals to.